Hello, welcome back to our second installment in Building Up the Fourier. Today we're going to talk about the orthogonality principle. It's going to help us out with some of the math we were trying to do last time. If you remember last time we started introducing this idea of using building blocks to approximate functions. Remember this p of t function that had a value of 1 between 0 and some period t of s and 0 everywhere else? In this case, we set our basis function to be that p of t, and we said that to do some approximation of x of t, which we call x hat, we're going to use a sum of scaled versions of the basis function. In this case, we're time delaying the basis function, so we have a whole bunch of different versions of that p of t. And we result in this dashed red line that it's our approximate version. But last time we ended with a couple questions. What is the best way to pick the scaling coefficients associated with the basis functions, as well as what basis functions should we even be using to do this approximation? Well, today we're going to introduce the idea of the orthogonality principle. We're going to call it OP for short. And we're going to say that the ISE, that integrated squared error we introduced last time, is minimized if and only if the integral of the difference between the function we're trying to approximate and that sum of scaled basis functions multiplied by the conjugate of the basis functions, all that in an integral, is equated to 0 for all k. And remember, k is the index on the different basis functions. So we're going to throw this at you. We're not going to prove it, although you can go back to your textbooks and find online proofs of this. We're actually just going to use it. And it's great. It's really helpful. You just have to watch that. If you don't do things properly, you can end up trying to solve n equations for n unknowns for n different basis functions. All right, so it is useful, but if you don't pick your basis functions carefully, you get a whole bunch of coupled equations, and they can look big and messy. So for example, if you have 1,000 basis functions, n equals 1,000, you're going to have 1,000 coupled equations. And this can take quite a while to solve, and it's not going to be very easy in some cases. So how are we going to deal with all these equations? Well, we're going to look at a particular case where our basis functions happen to be orthogonal. And what does that mean when basis functions are orthogonal? Let's consider two different basis functions, the ith and jth. And we're going to say that these two basis functions are orthogonal if when you integrate over time, the product of one of them and the conjugate, the complex conjugate of the other, will equal 0 if they're two different basis functions, and it will equal a constant if it's the same basis function. Okay, so we might get lucky and we might get orthogonal basis functions, or we could think about, maybe when we do our approximation, we should use basis functions that are orthogonal. Now, why would we do that? It's not exactly clear what's great about this particular property, but let's go back to all those equations, those coupled equations we were trying to deal with and solve for last time. Because if we solve for these minimizations, we will get our coefficients. Now, if two functions, basis functions, happen to be orthogonal, and you're integrating over time, the first basis function and the zeroth, or the complex conjugate of them, are going to end up with a 0 term. So this term multiplied by the complex conjugate of the 0 term, when integrated, should become 0. Same with the n minus 1th multiplied by the conjugate of the 0th one. This term and this term, well, that's going to produce a constant. So this term will be zeroed out, this term will be zeroed out, all the terms in between will be zeroed out, and this one will be left. And we know that one's going to be a constant by definition of basis functions being orthogonal. And we can apply that to all of our other equations as well. This one will be non-zero, but all the rest will be. And this keeps going. And what you'll see is there's only a few terms left. In fact, there's only 2 terms left in each one of the equations. And what's great about each one of the equations is the 0th equation has x of t term, and it's going to have this term. And if you look at each one of these equations, you'll see that the first equation can be used to determine C0. The next equation can be used to determine C1. The last equation can be used to determine C of n minus 1. They're the only coefficients actually appearing in each one of these equations. And so for the kth equation, you can get the x of t term times the complex conjugate in the numerator, and in the denominator, you'll get the kth basis function multiplied by its conjugate. If you don't remember where that came from, let's just go back one slide for a second, and let's look at the first one. There's only the two terms. If you want to isolate C0, you can break up this integral into a term, an integral of x of t times psi 0 star. The second term will have the C0 term with psi 0 times psi 0 star. And of course, it's not just for k equals 0, it's for all of the equations. And this is great because now we've got one equation for each one of our scaling functions. Sometimes we like to write it out where the denominator in the previous slide is represented by that constant, capital K sub k. Let's start an activity, and this one I'm going to get you to help me with. Just like in the previous lecture, we've got a given and find problem that we're trying to accomplish. We're given a sawtooth function to approximate. We're given a couple basis functions for k equals 0, k equals 1. So there's only two non-zero basis functions here. One is the original p of t. The other is a shifted version that's actually flipped. And in this case, the periods are only half a second. And what we're trying to find is the scaling factors for each of these two basis functions. What do you think these two basis functions look like? Pause now and see if you can draw them out. Get a piece of paper, get a pen, try to draw out these two basis functions. Then pause the video. When you're done, start the video up because I'm going to flip to the next slide. Are you done yet? Okay, let's go to the next slide. You can see the two basis functions. Each has a period of 0 to 0.5 seconds. The first has a height of 1, second has a height of -1. And again, what is our problem? We're trying to find the scaling factors of each of these two basis functions to best approximate that sawtooth. I want you to pause the video again and see if you can write out what is the best way to calculate C0 and C1, given that we've got the orthogonality principle working for us. Take your time. Did you write them out yet? Okay, let's go to the next slide to see if you got the answer correct. There we go. We can write out that equation that we derived or talked about a few slides ago, and we want to use this equation to find C0 and C1. Okay, so let's calculate that constant for C0 when small k equals 0. We can start substituting in, but let's let you do it first. See if you can substitute the correct values in. Have you done it yet? Okay, I'm going to go for it. The first basis function has a value of 1 between the times t equals 0 to t equals 0.5. So we can integrate that pretty easily, which will give us a value of 1/2. What about for the next basis function? Pause the video and see if you can calculate it. Let's calculate the denominator for this next basis function. You can sub in, it had values of -1 for the time span of 0.5 seconds to 1 second. Do your integration, and you will also get a value of 1/2. Let's keep going. I think we still have the numerator in both of these coefficients to calculate. Before we give the answer, see if you can plug in the appropriate values for x of t and the complex conjugate of the basis function, and see if you can come up with your final coefficient values. Pause the video, please, and go for it. Are you done? All right, here goes. C0, after substituting in 0.5 for capital K sub 0 and putting in the value of t and the complex conjugate of the basis function equal to 1, doing all your numerical calculations should give you a value of 1/4. Okay, go for C sub 1 now and see if you can get it. Are you done C sub 1? If not, pause the video. Otherwise, let's see what I got. Well, I got a value of -0.75. So I just calculated my two scaling coefficients, one for each of my basis functions to try to approximate x of t. if I plug these values in, this is what I get. Does that make sense? I took a quarter, multiplied it by 1 for the first basis function. And the second basis function was negative down to -1, and I multiplied it by a scaling value of -3/4 to get this. Does that look pretty good? It's better than the last video, and you might start to get some intuition. Hey, you might want to use more than one basis function to get a better approximation of a continuous valued function. So we did pretty well there. Let's summarize what we did to do that approximation. First of all, we took note of the orthogonality principle to help us determine the scaling coefficient values of ck. Now that could have led to a whole bunch of equations to solve, but we chose a particular set of basis functions that were orthogonal, and that allowed us to decouple the equations and gave us one simple equation for each basis function scaling value to calculate. Now, we still have not determined what function should be used for basis functions, except for that we know they probably should be orthogonal, because that's going to help us out